Alkylation of 1,4-dimethoxybenzene. The purpose of this experiment is to synthesize a tetrasubstituted benzene derivative using a tertiary alcohol and H2SO4 to produce the electrophile in the aromatic substitution reaction. Extraction and recrystallization will be used for purification of the product. The substitution pattern of the product will be determined by its final melting point and NMR spectra. Friedel-Crafts reaction is useful for synthesizing carbon-carbon bonds. Aromatic compounds can undergo electrophilic aromatic substitution by forming delocalized cationic intermediates. The electrophile is a tert-butyl carbocation in this alkylation of benzene reaction. Dialkylation is what we see in this reaction. This happens because the tert-butyl group that adds to 1,4-dimethoxybenzene is a mild activating group that will result in the addition of another tert-butyl group to the ring. Both the methoxy groups are also quite activating, which makes the entire reaction proceed faster. Here we can see that 1,4-dimethoxybenzene will react with 2-methyl-2-propanol, also known as tert-butyl alcohol, in the presence of sulfuric acid to create two separate isomers, the first being 2,5-ditert-butyl 1,4-dimethoxybenzene, and the second being 2,6-ditert-butyl 1,4-dimethoxybenzene. The 2,5-ditert-butyl 1,4-dimethoxybenzene is a major product and will be seen as a solid. The 2,6-ditert-butyl 1,4-dimethoxybenzene is the minor product, presenting itself in liquid form. The reason this is the minor product is because the tert-butyl is bulky, so it might inhibit the formation of the 2,6-ditert-butyl isomer, because then three bulky groups would be right next to each other and contribute to major steric hindrance. As you can see, the tert-butyl carbocation comes from the removal of a protonated alcohol from tert-butyl alcohol in the presence of sulfuric acid. This carbocation is easy to form because it's a tertiary carbocation. The delocalized cationic intermediate for dimethoxybenzene has two resonance forms. This stabilizes the intermediate, making it easier for groups to add to it, and speeds up the rate-determining transition state step. The electron-donating methoxy groups on benzene speed up the substitution process as well. Excess tert-butyl is being used, so two electrophilic substitutions occur, leading to the production of a tetrasubstituted product. The first technique being employed in this experiment is microscale recrystallization. Use this technique for less than 300 milligrams of solid. First, dissolve the solid in the flask and boil it to remove any impurities. If colored impurities are present, cool the mixture and add activated carbon decolorizing pellets, norit pellets. Lastly, slow cool the mixture and collect the recrystallized solid through vacuum filtration. Use a 10 or 25 milliliter Erlenmeyer flask as the filter flask to collect the filtrate. Use a Hirsch funnel to collect the crystals. It is important to slow cool the mixture prior to filtration so that the crystals are pure. Hasty cooling can lead to impurities being trapped in the crystals. The second technique being used is microscale extraction. Use a conical vial or centrifuge tube to hold the two-phase mixture. The tube can be spun in a centrifuge to produce a clean separation. The V-shaped bottom of the centrifuge tube enhances visibility of the interface between the organic phase and the aqueous phase. Use a Pasteur pipette to separate one phase from the other and then transfer it to another container.
Part 1 of the procedure is as shown. For step 1, in a 10 milliliter Erlenmeyer flask, add 140 milligrams of 1,4-dimethoxybenzene and 0.25 milliliters of 2-methyl-2-propanol and 0.5 milliliters of acetic acid. Step 2, briefly warm the solution to dissolve the solids. Step 3, clamp solution in an ice bath. Step 4, while stirring, add 1 milliliter of H2SO4 dropwise over a 1-minute period. Step 5, to stir for 5 minutes. Step 6, let the solution stand for 10 minutes. And then step 7, follow the following instructions for solid or liquid product. The procedure for a liquid product is as shown. Step 1, add 2 milliliters of diethyl ether. Step 2, transfer and rinse the flask into a large centrifuge tube. Step 3, remove the lower aqueous layer with a pasture pipette and place in 25 milliliters beaker. Step 4, add 2 milliliters of water and sodium bicarbonate. Step 5, wash ether layer with water. Step 6, remove the aqueous layer. Dry the organic layer with anhydrous sodium sulfate. Step 7, let the ether evaporate. And step 8, collect data. The procedure for a solid product is as follows. Step 1, wash the crude solid 3 times with 1 milliliter portions of water. Step 2, wash the crude product twice with 0.5 milliliter portions of ice-cold methanol. Step 3, transfer the crude product to a 10 milliliter Erlenmeyer flask. Step 4, recrystallize the crude in a minimal amount of ethanol. Step 5, collect the solids in a Hirsch funnel. Step 6, let solids dry. And step 7, collect data. Calculations. Because this reaction is 1-to-1, it can be assumed that all of the 1,4-dimethoxybenzene was converted into the product because it is the limiting reagent. Assuming 150 grams of product was obtained, the percent yield is around 66.67%. The product's melting point was around 104.5 degrees Celsius.
For IR of alkylation of 1,4-diterbutyldimethoxybenzene, we see two stretches, which represents the sp3 hybridized carbon-carbon bond. And looking at the proton NMR, we see A is the solvent, CdCl3, and B is the hydrogen on the aromatic ring, and C has an integration of 3, which represents the methyl group on the methoxy, and D has an integration of 9, which represents the tributyl group. Looking at the COSY NMR, there is no cross peaks, which means that there is no hydrogen next to each other, and it corresponds to the proton NMR. Looking at the C13 NMR, there are 6 peaks in total. Carbon 1 has a chemical shift of 152 ppm. Carbon 2 has a chemical shift of 135 ppm. Carbon 3 has a chemical shift of 111 ppm. Carbon 4 has a chemical shift of 55.9 ppm. Carbon 5 has a chemical shift of 34.7 ppm, and carbon 6 has a chemical shift of 29.9 ppm. And for depth 90 NMR, only carbon 2 with a chemical shift of 112 is there, and it is the assignment of CH, which is the carbon on the benzene ring. Looking at the depth 45 NMR, it has 3 carbons shown, which are 1, 2, and 3. For carbon 1, it is the methyl group on the methoxy, and carbon 3, they are the tributyl group. Looking at the depth 135 NMR, which shows the same result as depth 45 NMR, and these NMRs prove that the compound is 1,4-diterbutyldimethoxybenzene. And this is the end. Thank you.